Yes, Feroz, we can see your slides.
Perfect, thanks.
So Feroz, we didn't know when your call was going to finish. So we are starting at Preeti, Sunil,
Right.
Lakshmi, and then you. Will that
Okay,
be fine?
perfect.
Yeah?
Yeah.
So I'm letting people in on Zoom as well. Good morning, everyone. We are just waiting for some more people to tune in. We'll give them a couple of minutes. Okay, let's start with just a quick housekeeping instructions for everybody. Hi, everyone. Today we have a CTIS session, and I hope you all know what that stands for. But before we go into that, please make sure that if you're watching on YouTube or Facebook, you put your questions in the chat there. And if you are watching on Zoom, you have the Q&A box. Please put your questions in there. And if you would like to ask your question, please do raise your hand. And that's just a little hand icon that you'll see on your screen. So that's all. And I'll hand it over to Debarshini Chakrabarti from CCAM, who will introduce you to everything.
Yeah, so thanks, Pavitra, for hosting today's webinar. Very good morning to you all, and welcome to this second edition of the CTIS Tech Platform Series. The CCAM Technology and Innovations Webinar Series, or CTIS, as some of you may know already, is an attempt to facilitate interaction with the people behind our many programs and facilities. And the CTIS, or CTIS Tech Platforms, is a focus series under that same umbrella. And through this Tech Platform series, what we are trying to do is bring a set of talks on the various cutting-edge tech platforms that are housed at CCAM and the Bangalore Life Sciences Cluster, and their myriad research applications. And most of you are aware that Center for Cellular and Molecular Platforms, or CCAMP, is one of India's most exciting bio-innovation hubs, where we promote cutting-edge research and innovation in the life sciences. More on that later. And CCAMP is a part of the Bangalore Life Sciences Cluster, a triad of excellence in biological sciences, research, translation, and innovation in Bangalore. And this second edition of CTIS, we will do a 360-degree view of modern bioimaging. So quantitative imaging, as most of you know, is at the heart of modern biology. And there are diverse techniques ranging from high resolution confocal to electron microscopy to microtomography to X-ray crystallography to even cryo-EM that are suited for diverse biological tissues and diverse scientific questions. And last but not least is state-of-the-art image analysis, which has also advanced by leaps and bounds in recent years. So today what we have experts from BLiSC, confocal, EM, micro-CT, and image analysis facilities to tell you more about these technology platforms that are housed with us, their applications, and your scope to access these platforms through CCAM. So with that, I now pass on the mic to my colleagues, Dr. Preeti Bhardwaj, Electron Microscopy, Sunil Prabhakar from Micro-CT, who will speak first, followed by Dr. Lakshmi Balasubramanian from Image Analysis and Dr. Firoz Mustafa from Confocal. But first to Dr. Sheetal Kalme, Business Development Manager of Technology Platforms at CCAM, who will give you a very brief introduction to what we do at CCAM. So over to you, Sheetal.
Hello everyone, welcome to today's session. I'll just give a brief outline of what technology platform we have to offer as services through CCAM. Just give me a minute to share my screen. Hi. So CCAM is Center for Cellular and Molecular Platforms. As Debashini told you, we are part of Bangalore Life Science Cluster along with NCBS and NSTEM. And with CCAM being having two wings of bioincubation and services, in technology platform and resources, we have more than 12 technology platforms offer the services and training. Starting with, we have flow cytometry for cell sorting and cell analysis, micro devices for microfluidic and microfabrications. Genomics, we have next generation sequencing and Sanger sequencing as well. In mass spectrometry, we have divided mass spectrometry in 5 divisions for proteomics, glycomics, metabolomics, lipidomics, and biologics. In microscopy, where we have more detail today, we have confocal and super resolution imaging. Electron microscopy, we have scanning and transmission imaging. And we also have atomic force microscopy. In structural analysis, we provide services in NMR with 600 and 800 MZ, X-ray crystallography, cryo-electron microscopy. In transgenic animals, we have mouse and Drosophila. Currently, we are dealing only in embryos in mouse, but we'll start soon be providing the service for animals as well. Then we have a high throughput assay and high content imaging analysis as well with us. Along with these, we do also provide gene synthesis, cloning, expression, and purification services as well. And this concludes my talk. I just wanted to tell you that doesn't matter what your sample is or what source of your sample is. Matter is what technology will be helping you to get the results, kind of results you are expecting. If you don't know what technology platforms to be used for your kind of application or results which you're expecting, please contact us and we'll be able to help you with these technologies. Thank you again. You can visit our website www.ccam.us.in for more information about incubation and the services and the machines available with us. You can write to us on services@ccam.us.in for more information or regarding any quotation or pricing or any other services and trainings at services@ccam.us.in. Thank you. Over to you, Debashini.
Yeah, so thanks, Sheetal, for the great introduction. I now invite Dr. Preeti Bhardwaj from Electron Microscopy Facility to please tell us more about her platform.
Hello, everyone. Now I will share my screen. Just wait. Just
Preeti, you can press the icon in the bottom right corner.
Yeah. Okay. So I think it is visible now to everyone.
Yeah, but you're not in present mode.
What you are saying? You are not able to?
No, it's fine, but you can put it in the present mode if you click the bottom right most icon.
Near the screen resolution, you can see the presentation icon. You can click on that. Right hand side corner. Down.
Now it is okay. Now it is okay.
You can press F5 also, Preeti.
Yeah, now it is okay. I think it is in presentation mode only now. It is in presentation mode?
No, Preeti is not.
Okay.
I think it's okay. Just continue. It's okay.
Hello everyone. Today we will talk about field emission electron microscopy. So first we should know what is microscopy. Microscopy is the technical field of using microscopes. Microscopes are the instruments used to magnify small things which we can't see with the naked eyes. So this is the scale which show different types of microscopes according to their resolving power and these samples for which we have different scaling. So based on their resolving power, the microscopes are divided into 4 subparts, that is optical microscope, electron microscopy, scanning probe microscopy, and the emerging is X-ray microscopy. So the electron microscopy are scientific instruments that uses a beam of highly energetic beams to examine objects on a very fine scale. It yields information about the topography, morphology, composition, and crystallographic information. Mostly we have 2 types of electron microscope. So that is transmission electron microscope, which allow us for the to view the inner structure of the sample, and the scanning electron microscope, which allow the morphological examination of the sample. So this is the comparison between light microscope and electron microscope, in which the source of illumination in light microscope is light rays. In electron microscope, the source is electrons. So the wavelength for light rays is 400 to 700 nanometer, while for electrons it is less than 0.1 nanometer. So the medium in light microscope is air, while in electron microscope we are working with electrons, so vacuum is required. In light microscopy, glass lenses are used, while in electron microscopy we will be using electromagnetic lenses. Image visibility, the images we can see directly the image which is formed, while in the electron microscope the image is formed on fluorescent screen and then we have to see it. The electromagnetic lenses or the glass lenses in light microscopy are focused by mechanical in light microscopy, and electromagnetic lenses are focused with electrical signal. So due to the difference in the wavelength of light rays and electrons, their resolving power changes, as resolving power is directly proportional to the wavelength of the beam. So the light microscopy wavelength is resolving power is 200 nanometer depending upon the wavelength. So in electron microscopy, we can go up to 0.2 nanometer. So now the working of the SEM, scanning electron microscope is same as the light microscope, with have condenser lens, objective lens, and the sample holder and all that things. But yeah, it is divided into 4 subparts. First is electron gun, second illuminating system, third scanning system, and fourth is the detector chamber. The first is the electron guns are generated. Electron guns generate the electron at the top of the this chamber. Electron guns can be electron gun generate electrons from different filaments. It can be tungsten filament, lanthanum oxide, field emission gun. So there are different probes which are used to produce the electrons. Then the yeah.
Sorry to disturb. You are on the first slide. If you could change the slides you're talking to, you can click on that slide.
I am okay. From here, I am on working of the.
Because we can see only the first slide.
Okay, I will again share. I will stop share and then.
Yes, please.
Sorry. Stop. Is it visible now or?
No.
Sorry guys, I think it is taking time. I don't know why, but.
Preeti, could you maybe continue without the slides for right now?
Okay, if you people. Just give me 2 minutes. Is it visible now? Sheetal?
Yes, Preeti, we can see your slides.
Yes, go ahead.
So, which slide it is? Introduction or something else?
Electron beam and specimen.
Okay, that is fine. That is fine. So, we are discussing the, sorry for the disturbance, we are discussing the working of SEM. So yeah, the electron gun is the source of electron. So the electrons are generated at the top of the column. This hole is the column. So electrons are generated at the top, and it can be generated from the tungsten filament or lanthanum oxide or field emission gun. There are different probes we can use to generate the electrons. Then the electrons are controlled by the condenser lens and the amount which is traveled downwards. So it is controlled by the condenser lens. Then the objective lens focuses the beam into the spot of the sample. Here we place the sample, and this is the objective lens. The deflection coil helps in the raster formation of the image. This is the deflection coil. It helps in the raster movement of the image formation. Then we have different types of detectors, backscattered electrons, secondary electrons, CTIS. Different types of detectors are there depending upon the requirement of our imaging. So this is the basic flowchart of the scanning electron microscopy. Now the electron and beam interaction. In the sample and the electron beam interact. So it produces number of signals. This is our primary electron beam, which and this is the sample. So from this interaction, secondary electrons that gives the topographical information, and these electrons will be from the scale of 100 nanometer approximately. So the upper region with so the information, topographical information is there. Then second, backscattered electron. Then we have X-ray source and cathode luminescence agar. So there are different types of signals we get from the electron and this sample interaction. These are inelastic scattering also happens, and elastic scattering also. So in the SEM, we are focusing on these signals. These signals are imaged while using transmission electron microscopy. So the electron beam and sample interaction depends upon accelerating voltage and the atomic number of the sample elements which have. So it increases, the interaction volume increases with increasing the accelerating voltage. As you can see, this is the electron beam of same there. Low accelerating volume, low interaction, and it increases with the high voltage, while it decreases with atomic number. Like high atomic number have less this interaction, and a low atomic number have higher this interaction. In this image, we can clearly see the effect of voltage. This is the backscatter imaging of the tin ball at 5 kV, this one, and this is at 15 kV. With lower voltage, the carbon contamination on the top of the sample becomes visible. And when we increase the voltage, the deeper penetration enables the imaging of the top of the topographically information. So the information with 5 kV is better than 15 kV in the right. So we have to adjust this, that for which sample we have to look at which voltage. Now for a good imaging, the sample preparation is very important in electron microscopy. So for SEM, for normally biological samples are treated with fixatives, that is primary fixation, that is glutaraldehyde we use mostly, and secondary fixation is optional, that is with osmium tetroxide. While you are preparing sample for TEM, it is required, but in scanning electron microscopy, you can skip this step with lipids. Then the third is dehydration series with the solvent ethanol or acetone, because we don't want any water content in our sample. So dehydration step, we have to gradually do the ethanol and acetone streaming, that is 30, 50, 70, and then do up to 100%. Then we have to dry the sample. It can be done with HMDS, that is the chemical solution, or with a liquid CO2, that is with critical point dryer. For mostly biological samples, we go with the critical point dryer, and for cells and other things, we can use chemical drying procedure also. So for the basic requirement for the sample is that sample should be clean. No dust, oil free, nothing. It should be very clean. Then sample should be conductive. So most of the biological samples are non-conductive. So this is the main problem we will be facing. So we will give the answer to what we should do. But mostly biological samples are non-conductive. But for scanning electron microscopy, a sample should be conductive, and sample should be in dehydrated state. No water content should be there. So after this dehydration process, what is the principle of CPD? We will explain with this. CPD is like for CO2, this is the phase diagram with pressure and temperature. So there is a triple point in which solid, liquid and gases, three phases exist, and the critical phase where liquid and gaseous phase exists. So for CO2, this point is critical point is 31.3 degree as a temperature and 73 atmospheric pressure. So what happens when the sample is in 100% ethanol? When we put this our sample in the CPD, it flows the liquid CO2 inside our sample. So the ethanol is replaced by liquid CO2. After that, when the ethanol is replaced with CO2, then the chamber is warmed up to the critical point, this point. So the temperature is increased. So what happens is the liquid turns into the gases, and no phase boundary will be there. So no condensation or shrinkage will be there. Our sample remains like this only. So this is the best way for biological samples to dry them. Then this is the comparison for air-dried samples and CPD. So we can see that both the samples are same, but the pore size with air-dried comes out to be approximately 200 nanometer. When we go with a critical point, right, it comes to be 100 nanometer. So it maintains that. So this, you can see the shrinkage in water-fly. This is air-dried sample and this is critical point, right? So critical dry point is the best one. Then after CPD, we have to mount our samples. So mounting will be done on aluminium stub with a conductive tape. It will be the carbon tape or the aluminium paint, we can use both. So this is the carbon tape we have done. Both sides it is adhesive, so we can just paste on the aluminium stub and then carbon tape. Upon that, we have to place our samples according to orientation, whichever required by you. Okay. So, but we have to be careful that conductive paint that we have used. Sometime for liquid sample, what we use is we don't go for this carbon tape. We place the this aluminium paint, and then on that cover slip, glass cover slip is placed, and on that one drop of your liquid sample and then air dried. So the conductive paint should not come over the surface to be scanned. It should be underneath only. It shouldn't come on the surface. Second, paint should not lose its adhesive property, and it should not be able to withstand tilting, because while imaging you may wish to tilt the sample to some angle or something, so it should withstand that. So it should not lose its adhesive property, and it should make good electrical contact with both specimen and stub. Also, grounding is done with aluminium paint. We just have to paint this stuff with a little of aluminum paint we have to apply on this, so that do the grounding. Then also after mounting also, the samples are not conductive, so we have to make them conductive. So if we don't make them conductive, what will happen? Charging effect will happen. Charging effect is that the negative charge of the incident beam accumulates on the surface of your non-conductive specimen, like this. It will generate here. So what will happen, it means that your total number of electrons emitted are not equals to the number of electrons of your backscattered electron, absorbed electrons and secondary electrons, because they are generating there. So this is the problem, charging effect. When charging effect occurs, what will happen while imaging? You will see the brightness in the corners and you can't focus the image. So to overcome this, we have to do metal coating. So specimen is coated with a thin layer of 15 to 30 mm of a metal. Metal can be silver, gold, heavy metal. It should be gold, platinum or platinum. So what are the advantages of metal coating? It gives the conductivity to your sample, mechanical strength, and number of secondary electrons emitted from this specimen surface increases. And there are two methods for metal coating. One is thermal evaporation and sputter coating. Mostly people prefer sputter coating because it evenly do the coating. So this is the sputter coater instrument. These are the sputter coated stubs. You can see clearly gold is on this, gold is sputter. So earlier these are the samples which you have pasted on mounted. So after coating it should be like this. Now they are okay for the imaging. You can proceed with imaging. So there are some key points for imaging. Like if you want to go for high depth of focus images, rough surface, but that needs to be focused and that. So your angles, focus angle should be small. Objective lens aperture should be small, and you can work on long working distances for high depth of focus if you want an image. But if you want an image with a high resolution, so for high resolution images, you have to use this small probe size and low probe current. There should be no vibration, and you have to work with very short working distance. And you can use high brightness for this. These are the conditions for high resolution imaging. For EDS analysis, you have to increase the probe size and more probe current you require. Contrast is very important in this, but and contrast will be generated depending upon the the composition of the sample. So these are the some images of scanning electron microscope. This is the mice liver. This is the portal vein. This is the hepatocytes. This is the fruit fly foot. So this is, you can clearly see how they sit and that. These are the fruit fly eyes, compound eyes. This slide is shown. So these are the fruit fly eyes, and this is the some filter they have prepared. and these are the E. coli. So they want to know that how the filter is working and how much the bacteria they contain. So these are the E. coli they have contained. So these are the pollen, just like the COVID structure, coronavirus, and these are the human hair. So these are the different images with scanning electron microscopy as different current and different detectors. So in the scanning electron microscopy, which we have other modes also than normal scanning electron. We can go for energy dispersive mode that gives you information about the elemental composition, because every element have their unique inner shell and outer shell energy differences. So they provide the character sketch X-ray emitted from them. So based on this, they provide a X-ray character sketch, which we depending upon the energy differences, so we can identify which element is this. So the contrast is based on the atomic number. Higher the atomic number, the brighter will the image will be, and for the lower atomic, the dark image will be. And for second, we have the variable pressure. Variable pressure allows us for non-conductive samples without coating. Earlier, we have the problem of the sample should be coated, and so we have to go for sputter coating. But in variable pressure, what we can do is we can go for non-conductive samples and hydrated samples. And then the third is scanning transmission electron microscopy, that is STEM. It combines the principle of transmission electron microscopy and scanning electron microscopy both. So, but for this we have require ultra thin sections. So the sample preparation is altogether different. The sample preparation is similar to the TEM. In transmission electron microscopy, we have to, after dehydration, we have to do embedding and all that. Resin we have to prepare, and after ultra section cutting, grids are prepared. So these are the grids. You can see the copper grids are there. So on copper grids, we have the sample, our sample. So this is the stuff we placed in the scanning electron microscopy, and then the images are formed. So this is the one of the image of Drosophila eye, and we can see this. This is the inner structure. So it allows us the selection of specific diffraction angles or the directions of the transmitted electrons by adjusting various apertures and detection position. So it gives us the advantage over normal transmission electron microscopy. Then we have cryo scanning electron microscope also. For cryo electron microscopy, the one advantage is that you don't have to process your samples. You can directly image your samples. So what happens is, whatever your sample is, it is frozen in a preserved state with the liquid nitrogen. Okay. And then transferred to the cryo preparation chamber onto the cryo stage under the vacuum. Then we have the knife in that cryo preparation chamber only. With that, we can cleave the sample, and we can show that which portion we want. So we can cleave the sample. After that, we can the sputter coating can be done inside the cryo preparation stage only. So at that stage only the sputter coating will be done, and then you can do your imaging. So with the cryo SEM, this is the Drosophila compound eyes, and this is the plant leaf structure. So I would like to acknowledge Dr. H. Krishnamurthy, facility head, FACs, and Sunil and Anjana, team members, Dr. Sheetal and Ashok Rao, and our instrumentation and lab support team.
Thank you, Preeti. Sheetal, you were saying something.
Yeah, I don't know.
Yeah, please go ahead. Sunil will be presenting now.
Yeah, there is presentation. Oh, any questions? Hello.
Yes, please.
Hello. So we can go with question answers.
No, we will be going at the end of the all the talks. So we'll
Okay.
go ahead with Sunil's talk now.
Okay, okay, no problem. Okay, I hand over the mic to Sunil.
Hello, am I audible here?
Sunil, go ahead, share the screen.
How do I put this? Oh, here, yeah. Yeah. Hello, am I audible here?
Sunil, you are audible. Please share the screen.
Yeah. Give me a minute. Yeah. Let me just.
Yes, just click on the green button saying at the bottom of the screen saying share screen.
Yeah.
Then open your presentation on laptop and then say share screen. Yeah.
Yeah. I've opened the presentation. This is rather slow here. Okay, there is Shift F5. Can you see the slide here? No, you can't see the slide yet, right?
No, we're not.
Okay. Hang on a moment. I'll now. So, where is the Zoom? Yeah. Okay. So, okay. Okay. Yeah, I have opened it. I don't see the Microsoft PPT screen for sharing, Sheetal. How do I?
Zoom, in the Zoom, you can see the green color button at the bottom, share screen.
Green color button, okay.
Share screen, yes. Yes.
Okay, this one, right? All right. So now I. Okay.
Not presented yet.
Okay. Can you see the slide now?
Not yet.
Okay. So it is saying Zoom is sharing the window. Stop sharing.
Just do stop sharing.
Just click on the PPT.
I have clicked on the PPT and it is. I'm changing slides now.
No, Sunil, I think it's taking time. What we'll do is we'll start with Lakshmi and then we'll come back to you. You can stop sharing, Sunil.
All right, I'll do that, yeah.
Yeah, we'll start with Lakshmi and then.
Okay, I have stopped sharing here. Okay.
Yeah, thank you, Sunil. We'll start with Lakshmi. Lakshmi, you can please start your presentation.
Yes, Sheet. Just give me a second.
Preeti, you can mute yourself, please.
Yeah, I'll do that for her.
So you're able to see my screen?
Yes, Lakshmi, we can see your screen.
Okay, I'll start.
Yeah.
Good morning to everyone. Thanks for attending this session. Hope you will be beneficial at the end of the day. I'm Lakshmi. So I'm a consultant in CCAMP. I do take the bioimage analysis part. Anyway, we are having a good amount of time to discuss at the end. So I'm just going to not just highlight what is the bioimage analysis. So it's just a picture of a scenery that you are seeing. So many times, so already Preeti had given some introduction on EM, and you're going to hear a lot more from the imaging aspect from Firoz. It doesn't matter where the images are coming from. Of course, the source of the image is important in the context when it comes to quantification. So this is a scenery that is taken in a normal camera. It could be anything. What is the image analysis? Sometime when you do some adjustment, when you do a brightness and contrast, do you call that as analysis? Definitely not. The all about bioimage analysis is measuring or extracting some information. Basically, most of the time what we want is in the very basic level, you want to measure something. What is the size of this object? What is the size of this area? So in this picture, if I want to measure what is the size of this lawn, can I count the number of trees inside this lawn area? Is there any houses or building I can see? Will I be able to find it? Just this is what an image analysis is. Generally, to measure something or to extract features, we call technically. It could be measuring something, count something, or locate where it is. It's on its own. The list goes on and on. Definitely, just adjusting the brightness, contrast is never an analysis. That is just for us to visualization. So I no need to highlight upon this. This is a well-known thing in life sciences. You always have a scientific question. You start with a model system. It could be animal or your cell culture. You do plate the cells and do imaging. So imaging could be from any technique, a confocal, a normal widescreen or EM, and you have the images at the end. So now, most of the time my role starts here. So many a times you have lots of images. It could be a lower level analysis or a high content analysis, a lot. Then you want to extract something from the images. Yeah, so this is a whole journey of your generally very gross level a scientific project that you would be looking on. So if you look at, there are many portions in this journey, right? So many times I always suggest while you want to do the image analysis, be sure about the choice of the system that you want to choose. As Sheetal pointed out, when you are not sure which technique to go. So this is my scientific question. I don't know whether should I go for a confocal, should I try to look for a tracking studies, or a simple basic 2D image will do for me, or should I go for a high-end EM images? Please reach out to us to if you're not able to come or make out which technique will be good, because that matters a lot for an image analysis. I always say that spend a lot of time which technique to choose and which machine to use and what is your resolution should be. Will this resolution will be helpful to answer my scientific question? Yes, so if those are the things one should keep in the mind while you are imaging. Once you have the images, yeah, you have a lot of ways to do work on it. So all these things boil down to your scientific question. What is the question you're trying to ask? What you're going to look from the image? What are you interested to just count the number of cells in that field of view or in a particular well? Or I'm going to see some kind of a texture, or I'm going to see some kind of a punctage or any other, morphological changes, then you should have the images or, the technique that you use should be used appropriately. So then image analysis is more or less easy actually task to do. So how to do the task? There are a lot of ways. So I'm just put out the screenshot of the free tools, image analysis tools available. This is from the open image analysis forum that is been, you can search, go to this forum and ask. So there are so many tools available. So this is not the end of the list. There are many more. This is a pool, I would call. These are all free tools, so you can download and use. Most of the times in the perspective of life science, you're asking normal research questions that we are trying to ask, the free tools should be able to answer. So you can always, I suggest people to go to this forum and have a look at it. There are individual communities who look into these each of the softwares and try to answer the questions people ask from how to open an image in the software, what is the software about. So you have an enormous lot of information over there. And just to give you a glimpse of this, there are so many icons that you saw, right? So what is all, why there are so many tools? Yes, there comes some time you need a special skills to work or to do or extract the features from the images. Is not all softwares, or if you ask me, can you tell me a software that can work for my all my to address my all my projects? Yeah, it depends on the project. Sometimes there is no single software I can point out to you that will help you to work out with all kinds of images from different techniques. Most of the time it will be the combination of tools you might have to use based on the question you're asking. So that is where so much of so many icons, for example, Fiji or Image, if people have used, most of them are aware of, which is a very common tool which can be used for many types of analysis. For example, I'm just pinpointing a couple of things. So there is this QPath, which is meant to do the quantification or work on the histopathology images. It's really, so they have built the software tool only based on the histopath. So it really works well for that. If you ask whether this QPath will work for the EM image, I will not say technically the answer is not no. Yeah, but you have a better one. You have something called as SpyEM, which will work for EM images. And you have some other tools also to work for EM images. So for example, biofilm, if you have more images on biofilm properties to quantify them, you have a separate tool. Elastic is a kind of a tool which brings in a very simplistic graphical user interface machine learning toolkit to work on the images. And there is one beautiful software called Nine, which brings in integrate lot other softwares into a platform. It's like a open platform tool where you can bring in, say, I have done some part with Fiji, I have done some part with QPath, now I have to integrate the data from both. Yeah, Nine is there. So there are so many. So what I'm just telling is just a glimpse. There are many tools for visualization itself. When it comes to a 3D quantification, 3D visualization takes a huge amount of a role. So there are a lot of 3D visualization tools available meant for that. I just wanted to pinpoint one more thing. There are, apart from this open softwares, there are web client servers also. So what is this web client servers? If people are aware, I just want to highlight upon on this. So this software, so these servers are, they are located somewhere in the globe, and what you need is, you need to have an access, like, how we have access to our social medias and other login. So that will create a small user space for you, and you can log into that server, and there are multiple common softwares which are installed in that. So what is a big advantage of this? You don't need to worry about the computational power that you have. Many a times in the universities and in some places, you may not have a good computational power to use. So these are really best. So what you need is a good internet, and I think at least for the past 1.5 years we are really good with that, getting a good network. So that is enough to build. So you can right from visualize your image, build your pipeline, run the data, and do the quantification. quantification. So everything can be done in the, I have put some of the popular web servers which can be, or which is popularly used. I'm just going to highlight upon what we do in CCAM. We do give image analysis training in the 2 levels. One is a basic course that we conduct. So it's a 3 days course, which includes significant amount of discussions and assignments, and where you can try to come up with your workflow for your own projects. And in the basic course, what I highlight more is very basic concepts of images. Once you have the images from the microscope, even little bit of basic how those digital images are being generated, and what is the image is, and how will you analyze right from opening the image. So you don't need any background knowledge. So we start from there and try to go till concepts like what is a background, what is your foreground, how we can get rid of the background, a few other, very basic kind of batch processing. How can you do, say I have say 50 images, I have some couple of steps to run, how to do it quickly. So these kind of topics is what we cover in the basic course. And we also have another level of advanced course. So in the advanced course, I would say that little bit of a knowledge on images, and especially with respect to the microscope images, will be really beneficial to work. Otherwise, I will just generally recap on the basics for a couple of hours, then go about it. And we cover more advanced segmentation methods and registration, more on the 3D quantification, more on the automated script writing for image analysis. So these are the the overall topic that we cover in these 2 courses. So the advanced course is coming up in May, for which the registration is still open. You guys, if you are interested, please go through it. And apart from the trainings, we do some services. So one is, I would say that we are doing one-on-one consultation with some prior appointments, or you can just write to us and we can fix up some time to consult. Say I don't want I want some suggestions how to go about it. I have this kind of a data set I want to give a try on my own, or what could be the best tool. So if you just want to understand how to go about it, yeah, we can go on consultation. You can write to us. And we are also doing services if you want. So along with the images you have taken, so right from your sample, you can send it to CCAM. You can choose the technique for imaging. Once your images are there, you can, we are open to build up the workflows and pipelines for you. So we are generally, we can, I would say that if you give me an image, you tell me what you want to extract from that, I think I can take it from there. I won't refine saying that this type of image, yeah, as I said, each stands on its own. That should be only thing which I always request from the clients are, tell me what you want. So that is what I want from you guys. So what do you want to get from the image? If that is clear, building the workflow or figuring out which tool to use, it's not a big question. And we are also open to set up an automated workflow for high content screening data. So many times there are the screening platforms available. What I mean by setting up an automated workflow is, so if you're going to have a lot of data, or you're going to have, say, a lot of screens to work, and the similar kind of assays. So an assay can have many experiments, and you many times, technically speaking, you may have to have a similar workflow to work with. So once you have the screens, once you set up the workflow, you just take the images, put through the workflow, get your data out. And what will you do with the data? Yeah, we can do the data analytics also for the data that you had extracted from the images. And we do other histopath analysis also. So, I mean, that's all about image analysis. I can stop here. I think we can discuss rest on the discussion and QA session.
Thanks, Lakshmi. I would now request Dr. Firoz Mustafa to please take over. Firoz, if you are.
Thanks, Debashini. 1 minute, let me just share my screen. Yeah. Okay, so I would like to introduce the Central Imaging and Flow Cytometry facility at the Bangalore Life Sciences campus. So we are a common facility set up between National Center for Biological Sciences, Institute for Stem Cell Science and Regenerative Medicine, as well as the Center for Cellular and Molecular Platforms. So we provide imaging as well as flow cytometry access to users, both inside and outside the campus. So here, I think we are focusing more on the imaging part of it and the confocal microscopy. So I will not be going too much into the flow cytometry. So this facility was started to understand the different scales of organization in biology. And I mean, when we started, the campus had started to understand that there was a interest in looking at nanoscale and microscale biology, which is not easily accessible through other techniques. And optical microscopy was supposed to be one of the best ways to look at these, apart from, of course, electron microscopy. And similarly, for sorting and purification of cells, as well as analyzing cells through flow, was also started. So our goals are to run a state-of-the-art operator-free facility. This is for users in campus. For users, external users who approach us, it is a operator-assisted facility. So we help you with the imaging. We do training programs for both internal as well as external users. External users, mostly it is for the flow cytometry. For the microscopy, we run a Bangalore microscopy course once a year with an intake of about 24 students. And unfortunately, this year we have been forced to halt it due to COVID. Both internal and external researchers can access the facility without any collaborations. We are also in the process, we also develop new optical systems in collaboration with researchers. So now, if you look at the kind of things that you want to image in life, it exists, it ranges from about a few centimeters to all the way to about angstrom, or even, about an angstrom. And in this, light microscopy is typically used in the hundreds of nanometer to the millimeters range. And nowadays, it's also being used in the centimeter range with the light sheet microscope. But typically, this is the range. And when you want to go lower, you tend to use electron microscope. And so the first thing is, what is confocal microscopy? Because we are focusing on confocal microscopy here. Confocal basically deals with having a con focus. So where you are focusing your excitation beam, you are getting it back and putting a pinhole at the back focus at the sample plane, at the image plane, so that you are only collecting from the specific point that you are interested in. And typically you do that by putting a pinhole aperture right in front of the photomultiplier. So what you get is that when you use a focused laser beam in the sample, you get an airy disk profile at the back focus. So this can be imaged using a pinhole. And so just from the width of this airy disk, you can get what the resolution that you get is. Typically, a confocal microscope will have a similar resolution uh, to the wide field microscope when it comes to XY resolution, and a much better resolution in the Z direction. This is assuming that you are looking at particles which are well separated from each other. Now, as you bring them closer and closer together, as it so happens in biological systems, in the wide field microscope start losing resolution in XY because the amount of Z-plane noise starts to swamp the signal and your contrast goes down quite a bit. So that's what you see here, where in the top images are images where it's been imaged with a wide field fluorescence microscope, and the bottom images are where a confocal microscope is used. So what's happening here is that in the top images, you are seeing the plane that you want to see, but there is also a lot of background light from both above and below that planes. Whereas in the bottom images, you are only seeing the image you want to see because the pinhole is cutting off all the out of focus light and thereby giving you a better resolution. I mean, by giving you a better contrast. So apart from this, we also have things called super resolution microscopes. Confocal microscopy is limited by the diffraction limit, which leads you to around 230 nanometer resolution in the XY plane using GFP. But what if you are interested in looking at things which are smaller? So recently, over the last couple of decades, there have been new advancements which have increased the resolution, which have made it possible to image at a much higher resolution. So these technologies like STED, SIM, PALM, and STORM make it possible for you to image at much higher resolution by making use of techniques to sidestep this whole diffraction limit. Of course, they have some disadvantages as well. Typically, they are slower, they can lead to more bleaching, etc. But that's a different thing altogether. So there are compromises, but nowadays it is possible to go to resolutions higher than what is possible in a confocal microscope. So these are the set of microscopes and flow analyzers and sorters that we have in the facility. So we have a few point scanning confocal microscopes. These are our workhorses and they run almost 24/7. Not nowadays because due to COVID, we can't keep the facility open overnight. But these are the very used systems. Apart from this, we have as super resolutions microscopes like the STED, the ARIScan, the SIM and STORM microscope, and of course the TURF scope, and also a wide variety of flow analyzers as well as sorters. So all of these systems are accessible for external users. In case you want to use them as a one-off, one of us will be here to help you with it. These are our staff who run the facility. And thank you. If there is any specific question you would like to ask, please do write about it. Thank you.
Thanks, Firoz, for telling us about SIF. Is Sunil, are
yes.
you?
Yeah. Yes, he will be presenting now. He will be presenting through me. I'll just share the screen. Can you hear us?
Yeah, we can hear you.
Yes.
Hi, am I audible here?
Yes, Sunil, you are audible.
Yeah. So shall we start here? Can you see the slides that I'm changing right now?
Yes, yes.
Right. So hi, I'm Sunil Prabhakar. I work in the Electron Microscope facility, and I'll be presenting the micro CT services that is offered as a part of electron microscopy, services, and primarily this machine works on the principle of X-ray computed tomography, which I'll be talking about in a short while. So before I talk to you about the nits and grits of the microscopy scanner and how it operates in our facility, I'll give you just a flavor of what it can do. So in the next slide, you will see a video. Sorry, you will see a video of a honeybee thorax. This is just the thorax part of a honeybee. You might, a lot of people might have seen the honeybee, flying around and reared in the colonies for bee and etc. So here, we through some staining techniques and the X-ray computed tomography, we are able to visualize the internal parts of the animal without having to do any dissection. So that's the long and short of the X-ray micro-CT scanning ability. And now, based on this ability, based on this feature of X-ray photons to penetrate through your sample and resolve the internal parts, as you see here in the video, I'll just play it again. We are able to not just visualize the surface, as you can see in grayscale, but also the internal parts, which is kind of pseudo-colored in red. And those are specific parts of the musculature that is present inside the thorax of the animal. Okay. So now let's get on to the basics of the machine. So here is the schematic of the apparatus that we have in the campus. This is a SkyScan 1272 X-ray CT scanner. As you see in the left, there is an X-ray source which starts, which emits a cone beam of X-ray, which is generated from a electron source that is hitting a metal target. And as you can see here, drawn in the schematic is the fly, which is sitting on a stage which can be micro-positioned to a few millimeters for the minute adjustments to bring the sample within the field of view. And then the X-ray image goes through a filtering process if the users require. For example, high density samples like a bone or some kind of a metal coated biomaterial or composite material, which requires higher X-ray energies to penetrate the tissue, requires filtering as well. So for that purpose, we have 6 position filters, which is selected according to the sample requirements. And then the X-ray image falls onto a cooled CCD camera going through a scintillator. So as I have mentioned here, the stage can travel, can make a vertical travel to about 70 mm, which means we can, in principle, scan a sample which is about 70 mm long. But these fall into certain kind of constraints, which I'll come in a short while. And in addition to this, the CT scanner also gives us an option to pan the camera. As you see, the words written, S is the side position of the camera, and C is the central position of the camera in the extreme right of the image. And the camera can pan actually 3 different positions and can cover up to 75 mm in width, which means we can scan, for example, we can scan a large insect or a water can or some such, which is about 70 mm in length and 75 mm in thickness. So going by, taking Firoz's lead about imaging in millimeter to centimeter scale, this facility in the electron microscopy, among the electron microscopy services, actually allows you to image in microns resolution, but with large objects up to about 7 centimeter in length and about 7.5 centimeter in width. So with this feature, we next go to what kind of resolution that the SkyScan can achieve, and this is done by something called automatic variable acquisition geometry. It is nothing but, as you have seen in the first slide, the scanner is just a benchtop equipment placed next to two monitors over here, and in this little equipment it is able to like accommodate imaging of 7 centimeter length and 7.5 centimeter in width. How is it able to do that while actually maintaining micron resolution, micron size resolution? So this is the answer to that. So in most of the conventional scanners, you see that the source and the detector are actually placed in a constant placed in a constant position, as you see in this picture in the right. And the object is moved leftwards or rightwards depending on what kind of magnification is required. In the scanner that we have here, this is achieved by dynamic means, wherein both the source and the detector can adjust to different positions in order to achieve magnifications from low range, which is up to 1.4x, up to a very high range, which is, up to 16x. So, and in addition to that, so which means the object which is shown here is to be moving in other scanning systems is actually stationary in our setup, whereas the source and the detector are constantly adjusting their positions in order to achieve the desired magnification. So what is the resolution that we can achieve here? The pixel size in the micro-CT scanner can go down to 0.4 microns, which is the factory limits, and it can go up to 21.4 microns at the lowest magnification. So with this kind of dynamic adjustment system, we have the option to scan an image with variable pixel size, but with automatic, but with the same magnification. And also for the same magnification, we have we can also image in variable pixel size. For example, if I have brought the image to the sample to a magnification of for about 10x, I can record I can do the scanning of the sample at 4 different pixel sizes. For example, 2.5 microns, 5, 7.5, and 10. So therefore, the user is able to determine the choice of resolution for scanning for a particular magnification. So now with this adjustment features, what can the scanner do in terms of different imaging modes? So here is an example of a mosquito of about 4 mm or so in length. And the magnification over here is close to about 12x, and the pixel size and the resolution is about 0.7 micrometer. As you can see, the mosquito is completely dissected, and we are able to look at its internal parts through the X-ray illumination, primarily the musculature in the thorax and some of the brain outlines in the head, and also some parts of the abdominal, segments as well. So what the machine can do here is to set up, divide the mosquito into 3 separate frames, and then choose an area of overlapping choose some overlapping area in order to maintain the continuity between separate frames, which is done automatically, and then scan the whole animal automatically. In addition to this, it also stitches the images, aligns the images in such a way that the reconstructed images appear as one continuous picture of the entire animal. So as I have mentioned here, the vertical span can go up to 70 mm, but this is highly limited by the magnification that the user requires. So the 70 mm, the highest span is usually achievable in the lowest magnification, and even the longest span is also achieved in the lowest magnification. If we want higher and higher magnification in the scanner, the source approaches closer to the sample, thereby giving some kind of a technical limit on the vertical span of the imaging area. Okay, so this is one imaging mode wherein a sample which is oversized, which cannot fit into one frame in the scanner, can actually be distributed into multiple frames, and the scanning can be achieved in an automatic and sequential manner. So this is another example of a different imaging mode of the scanner. Here the user has loaded multiple samples. As you can see here, there are individual thoraces of many flies, and the user can actually load the positions of each of these samples into a box, which is actually noting down the positions, and then just start the scan. So, and the scanner is able to automatically load every sample positions and complete the scan without any user intervention process. So, which means we can, for small samples, for example, this is an example of a Drosophila thorax. So we will be able to load multiple samples into the scanning chamber, and then use this imaging mode in order to sequentially scan all the samples in automatically. You can also imagine this for the soft tissues like larvae and other things. How these tissues acquire actually the X-ray contrast that you see here, I'll be explaining in a short while. Okay, and finally, the imaging mode. We have a provision of loading samples of multiple sizes, of different kind of sizes, into this automatic changer that is robotically controlled, and you will be able to load samples which is in the millimeter range using the leftmost stub that is indicated with the long pole, and a large sample, something like a mouse femur or a rat skull and things like that on the rightmost stub, and you can load all of them in the automatic sampler, and it is going to scan it is going to load each stub sequentially and finish the entire scan without any user requirement in the facility. So all we have to do is to just make sure that the scan settings provided by the user or the operator matches with the requirements of the sample. Right. So for the interest of time, I'm going to skip on this resolution enhancement feature, and I'm going to give you a quick idea about how the staining is done, or what is the preparation that is done for the samples in order to conduct this an X-ray CT scan. At the top, the first is the fixation process, which you normally do for any soft tissue, which is done using aldehyde or an acid incubation. Formalin, bone solution, and carnoy solution are the popular fixatives for soft tissues. For mineralized tissue like bone or cartilage or keratinized materials, people normally go for long-term preservation, which is done in alcohol. And these alcohol preserved mineralized tissues can be directly taken for CT scan. All we need is to just make sure that the samples are dried, or the water movement is arrested, by wrapping some parafilm or some such, as I mentioned in the solidification process. And then it can be taken to CT scan directly. For imaging soft tissues, you need to build some kind of heavy metal staining, which is typically done with iodine for musculature, and for something like brain tissues and some glands and connective tissue, we can use phosphotungstic acid. So the staining part is available in the facility. So the user is welcome to specify any kinds of requirements which is required for a particular tissue, and we provide the facilities in order to perform the staining in the facility itself, and therefore taking it to the CT scan subsequently. So the intermediate process of solidifying the sample is also available in the facility, as Preeti pointed before, through the methods of critical point drying, or by chemical methods, or air drying, as well as through some of the recent techniques that have been developed in the lab. We can also use like a Vaseline-based solidification in order to arrest the water movement, and therefore kind of rigidify the soft tissue which is already stained, and then take it to the CT scan. So please feel free to ask questions about how the staining methods are there and what is available in the facility. Okay, as after the scan is after the scan is completed, we go through the process of reconstructing the image, which is as I have showed here. You give a stack of TIFF images, which is nothing but the raw, which is nothing but the shadow image of the X-rays, and then you go through the process of removing different kind of artifacts that are usually found in an X-ray CT scan, which is listed below. We can go through these details in the Q&A later. And finally, we can finally the software automatically outputs a reconstructed version, which can be saved in the form of these image formats mentioned below. So here is an example of what the reconstruction looks like. So this is done in the CT Box, which is available also in the facility. One of the packages for the X-ray CT software analysis. You can see here that different perspectives of the thorax of the fruit fly here is clipped in order to look at the structures, look at the internal structures, and you can rotate in any form that is of interest in order to visualize the structure beneath. All right, so here's the same movie that I showed you in the beginning. As you can see here, there is some degree of animation here, which is given to the clipping process of the reconstructed image, and this animation is also actually can be done in the facility through the softwares available in the Bruker package. So I'm in the interest of time, I'm going to skip a few slides. This is an example of a mosquito larvae that has been segmented and whose tomogram has been reconstructed, as you can see, to produce different perspectives of the larvae. This is the coronal image. This is the transaxial image, the transverse image, as you would cut bread slices of the animal, and then this is the sagittal image. So, which means you will be able to navigate through the entire body, internal organs of the animal, as if you were taking it through a microtome section. So, this is again an example of rat bone, which has been reconstructed and then their trabecular network has been segmented out for the purpose of calcium mineral density measurement, which is called the bone mineral density. So here, as you can see, the colored parts and the gray parts can be separated out by software in order to measure the bone mineral density separately on these structures. And this is basically how it is done in the facility. We have these calcium hydroxyapatite samples of known densities, which can be scanned in the software using the same settings that is used for scanning the tissue of interest as well. And we then use that as a calibration in order to determine the bone mineral density. Now, the computation process is not just limited to the BMD measurements, but also we are able to do carry out a host of morphometric measurements like volume of the tissue and then surface area of the tissue, and some of the second order measurements as well, like the structure thickness and the structure separation with respect to the reference frame. And these are built-in packages in the Bruker software that we will be able to use in order to carry out morphometry as well as mineral density analysis for the tissue of your interest. With this, I would like to end my talk. I would like to thank Dr. Krishnamurthy and Dr. Preeti Bharadwaj, who has been very supportive to start this facility in the electron microscopy services. And then Dr. Sheetal Kalme for giving me an opportunity to talk in this session. And Mr. Ashok Rao, the head of establishment and instrumentation and lab support, and the biocluster for all their infrastructure and all the support. Thank you very much.
Thank you, Sunil. I think we can possibly now take up some questions. Sheetal, do you want to go through them?
Yes. So I would request anybody, if you have questions regarding any of the talks presented, please put all your questions in Q&A session. And you can also raise your hand, and once we finish the questions from the Q&A, you can raise your hands and we'll give you an opportunity to speak up and ask your question. Starting, first question is for Preeti. What are some precautions for performing EM?
So while for sample preparing for electron microscopy, we have different fixators like osmium and glutaraldehyde. So we have to be very precaution, because osmium is very toxic for our health and very carcinogen in nature. So while working with osmium, you have to work in a fume hood that is full ventilated and that area. So we wear your gloves, mask, and eye protected while handling with osmium. And secondly, the electron microscopy is very high electron energy is used. So that lab should be very secure and all that is there. And third is grounding should be done properly.
What should be the for sample to be imaged properly?
While taking the images for the sample, first is if you don't use gloves, then your fingerprints will be seen while imaging. So you have to be, means after you have done your mounting for this sample of SEM, and after you have placed your samples on the grid, you don't have to touch them with bare hand. So always wear gloves. This is the first thing you have to take care for good imaging.
Next question is, what is the minimum thickness of samples used in electron microscope?
Yeah, for
EMS.
For TEM, the thickness of your the ultra microtome is 60 nanometers for sample, and it can goes around 100. So 60 to 100 nanometer should be the thickness of your ultra thin section for TEM and for STEM also. while the sample size can be increased for SEM, it can go into the centimeters. But yeah, your resolution you want higher, so sample should be thin.
Hope Mohsin, that answers your question. Next question, I think Sunil can take it regarding micro CD for materials. What is the sample preparation?
Okay, so this depends upon the nature of the material. So if your material is a soft tissue, like we see in a lot of biological structures, they don't inherently have the ability to absorb X-rays. So we normally stain it with iodine, as I mentioned before, or phosphotungstic acid, or for example, mercury chloride. In the earlier days, mercury chloride along with two other compounds were used for fixing tissues. This can be of advantage for an X-ray CT scan as well. For other kind of materials like polymer materials or PVC or any kind of composite materials which have some kind of heavy metal arrangement or a very dense electron cloud shell, they usually give a certain level of X-ray contrast, and that is good enough actually to resolve the structures inside. I mean, the best example is actually the PVC pipe. If we put a PVC pipe in an X-ray scanner, we actually will be clearly able to resolve the internal sheet as well as as well as the outline of the pipe as well. And this is without having to stain the sample at all. We just have to place the sample inside. The same goes for mineralized tissue as well. As I mentioned, for the bones do not require any kind of staining. On the other hand, cartilages which are at the nascent stage of its growth require some kind of staining using phosphotungstic acid.
I hope Shivaranjani, that answers your question. Pavitra, if you could unmute her, she had raised her hand. And I will request everybody else who wants to ask a question, please raise hand. Pavitra, can we unmute Shivaranjani? Yeah.
Yeah, she can go ahead.
Hello, Shivaranjani, you can ask your question, or you can tell if that satisfies your query. I think she is not there. We take up a next question by Anju. Does the last mention, that is micro CT technique, gives more information than MRI?
Oh yes. Yes, the X-ray CT scanner that we have is a high resolution scanner, but this scanning is performed only for ex vivo specimens, meaning these animals have been sacrificed and they have already, and and it is then further processed for high resolution staining, high resolution imaging. In case of MRI, you will be able to get information about the live activity within an organ of interest or a region of interest, but may not be happening at the same level of resolution that we are imaging structures here. So these two are they are quite different when it comes to providing information. MRI can give you information about the live activity in an organ and region of interest, whereas the X-ray scanner we have is able to resolve internal structures with very high resolution in micron scale.
Anju, I hope that answers your question. Yeah, so Mohsin Raza's question we have answered already. If you have any other questions, please raise your hand and we can unmute you to ask your questions, or you can type your questions on the Q&A box. Thank you, Anju. Yeah, please go ahead. If anybody has any other questions.
Somebody called Suman Azmira from IIT Kharagpur had sent a couple of questions in advance. If she is online, can we ask her to come online and ask the questions?
Yeah, Suman, if you're online, please raise your hand so we'll be able to find out from the attendees and we'll be able to unmute you.
Okay, I don't find her in the attendees list.
Debashini, please go ahead and ask the questions. We'll answer.
Yeah, I will ask the question. So she has asked for opportunities, research, and scope of image processing in government labs. I think maybe Lakshmi can take this.
Sorry, can you come again with the question, Debashini?
Yeah, opportunities, research, and scope of image processing in government labs.
Opportunities and scopes. So government labs, I understand that it is either she's mentioning the CSIR labs or any kind.
Yeah. So she has sent two questions. First was this one, and the second she has asked one more question regarding CSIR labs. So I guess she is referring to CSIR labs.
Okay. So I'll answer this question first. Regarding the scopes, yeah, so image analysis is an emerging field actually in the life sciences. Now it's really coming up. The scope can from any images, I would say, not restricted only to the images from microscope, and in the field of agriculture quite a lot. People take the images from the field and you can process from there, which can be nowadays a lot of mobile applications are coming up, which can be given in the mobile of a farmer or who is a person who doesn't know anything, just have a mobile, click a picture, and it's going to give you the data there itself. So it and till high resolution EM images also have a till there you can do the image processing, and lot of avenues right from the small scale to the high end high throughput imaging. Just imaging is done, side by side analysis is also going on. That would be the scope, I would say, depending on the facility. Sometimes I know in our country a lot of CSIR labs is improving with the facility, but image processing aspect is slowly coming up. I hope it will be to a good stage in future. Hope I answered.
Thanks, Lakshmi. There is one more question. She's saying that Suman herself has asked. So she has asked, which is maybe you have already answered it. May I know the various image processing, general as well as in healthcare works that have been done in CSIR labs? I think you probably already answered the question.
Yeah, kind of. So general, so as I said, if you take in the perspective of the healthcare, a lot of now applications to work on the the very common healthcare problem people are addressing is cancer tissue images, the histopathology images. There are the things like even the mobile application, so which is reachable to any part of India. So you don't need a microscope. Only the doctor has to send the imaging can be done in a very well in an urban place, and just forward the message, so forward the image to a normal healthcare center in the rural areas, which the mobile application can give what is the size of the give a rough estimate for at least the clinicians to take forward, or tell the patient to go to the next step, not wait for results for 1 week and so on, like that.
Yeah, I think that definitely answers the questions. So are there any more? There is somebody who is asking, can we get a brief insight into how image analysis actually works?
Yes.
I think this is a pretty broad question, but I think Lakshmi, if you want to.
Yeah, it's so to answer, actually, it's a very, as you said, it's a very broad question. If you ask me how it works, you have to one has to understand what is the images. That is the main focus that we concentrate on our basic course. I spend really few hours in telling the participants what is the image, because that is more important to understand, to analyze it. How it works. Generally, I would call image analysis is a number game. Images are basically numbers. Numbers that are reflecting the signal from your specimen. As I said, just a simple analogy I would put, you take a picture of your friend in the camera, making your friend stand in a garden. Now your focus is on your friend. So you don't even worry about what is there, whether there is a bush behind or is there a nice flowers behind, but your focus is on the friend. So you always focus more on that and try to get a clear picture of the face and whatever the person is standing. And that is now so you will have automatically if you look at the image, you will have the person that your friend is standing will be nice in focus. Some things will be out of focus. So why you are calling something is out of focus is you are not able to see it clearly. So how you can say it, this is a very layman term I'm saying. You can represent, generally images are representation of the signal. So what is this signal and where it is coming from? It depends on the technology you use. You use a nice fluorescence microscope, whatever the fluorophore you're tagging with, that is what is your signal is. And that is a basic concept of image analysis. Basically, it is a number game. Images are numbers. So generally we play around with the image, play around with these numbers when we do image processing.
Thanks, Lakshmi, for this great answer, because that really clears up matters a lot. Does anybody have any question on confocal, please? Nothing?
Please raise your hand, or you can type your question in the Q&A box.
Can I just ask a question, Sheetal and Debashni, to Sunil?
Surely, please go ahead.
Hey, Sunil, I was really nice technique that you explained and take you through. I'm just wondering if there is a kind of a comparison that has been, it's something related to the earlier question. Is there some kind of a comparison that has been done between the technique that you had showed, the micro CT, and the MRI, even in some specific regions?
I mean, you mean in terms of resolution or in terms of the scale of imaging?
Not in the terms of scale of imaging, in terms of resolution. What other information I could capture from?
Yeah, definitely. Can I go back to my slides actually to give you an idea of what I can directly.
Sure.
Yeah. Let me bring my slides onto the meeting screen. Yeah. Okay. So let's go to the. Yeah. All right. Here I have many actually ideas too. This is the one. Yeah. So over here in the bottom left, you see that there are these are individual muscles, right? These are individual muscles of the located within the thorax, and you see these breaks between these muscles, right? So now, if you have to visualize this in a confocal image, under a confocal microscope, you have to first cut this, cut this thorax into half, because the laser beam cannot penetrate the entire, thorax. And second, you have to stain it with phalloidin. Okay, and then and the third, you will be able to see these fasciculations. This is about 200 to 300 nanometer range. We have achieved this in about 500 nanometer range, but also our Z resolution is also 500 nanometer range when compared to confocal, which is 800 nanometer range, and it doesn't get any better there. So in other words, the Z resolution over here actually is a step above improvement over the confocal imaging technique. In addition to that, we are able to resolve these breaks within the muscle along the entire length of the muscle. This is very, very hard to achieve in a confocal microscope, because you have to literally cut serial sections in a microtome and then combine them together. Okay, this is to give you the comparison between confocal and this. When I scale it up to MRI, okay, you won't be able to see these level of micron details in an MRI image. It's usually in tens of microns, meaning you will be able to resolve the, for example, if I go to the bone image, you will be able to resolve the, the outer contours of the bone, and probably how well the bone is located with respect to adjacent structures. But resolving the trabecular network, the calcified soft tissue within the bone, is perhaps not possible in MRI. Okay, here it is possible. It's not just possible, we will be able to separate it out from the hard cortical tissue of the bone and conduct our analysis of interest as if we have dissected out that soft tissue from the bone. That is the advantage of CT scanning. We can do a virtual dissection of our organs of interest.
Okay. Thanks, Arun.
Please raise your hand or put in the question into a question box if you have any questions.
I think, Sheetal, shall we try to close the session now?
Yeah, we'll wait for 2 more minutes and then close.
Yeah, okay, sure.
Taking this opportunity, I would also like to announce that we are arranging a micro CT workshop with Bruker and LabMate. BLiSC is arranging this workshop on 27th, from 27th and 28th of April. End of that is last week of April. Anybody would like to register for this course, please write to us on services@ccam.trust.in, or you can, I'll just put it the email address in the chat box, and you can write an email to us to get more information about this course. And there's a registration fee of 1,000 rupees including GST, and this will be for almost 2 days course. So please do register. You can write to us at microct2021@ccam.trust.in for any information regarding this this workshop. So we'll be giving all the real information about what all, how to use this machine for different applications. And we'll also have as we cannot take this course physically currently, we'll be although arranging this course physically as well, a hands-on course, but currently due to COVID situation, we are doing it online, but we'll be having an online demo as well for sample preparation and scanning in this course. So please do attend this course and register, and write to us on microct2021@ccam.trust.in. So still, if anybody has a question, please write it in Q&A question or raise a hand, or we'll be closing the session in 2 minutes.
Okay, so if nobody has any more questions, I would just like to thank everybody for making it to today's webinar. It was a very insightful session. I mean, we had some seriously interesting talks from Preeti, Sunil, Firoz, and Lakshmi. So I would just like to say here that a lot of you raised concerns on slides and whether there is a recording available. So for the recording, we are streaming live on YouTube and Facebook, CCAM YouTube and Facebook pages. So you can catch the entire webinar there. We are not going to take down the file. So you can catch the entire webinar there whenever it is convenient to you. And for the slide deck, we would just like to say that we send out an acknowledgement mail to everybody once the webinar is over. So you will get that in a couple of days. Slides, if any, will be shared as an attachment with that mail. So I hope that answers everybody's queries. And finally, I would just like to say that like Sheetal had mentioned training programs, and I think Lakshmi mentioned training programs that are coming soon. Firoz mentioned training programs. We would just like to take this opportunity to remind you to please follow us, follow CCAMP on social media for various training announcements on various different programs, not just these 4, but on a lot more as well. And please follow us on CCAMP social media. You can follow us on Twitter. Our handle is CCAMP_Bangalore. You can also follow us on Facebook, CCAMP Bangalore, or LinkedIn. So I think with that, I would just like to thank everybody here, including Pavitra and Sheetal for coordinating and hosting this webinar. Thanks Firoz, thanks Preeti, Sunil and Lakshmi. So shall we close the session today now, Pavitra?
Yeah, thanks everyone. Have a good afternoon. Bye.